from the first one.
Yeah. Okay. So to turn a bromine into an alcohol, we want to use the OH. Is it the OH minus or the OH? That thing, that like weird thing we'd use.
Uh, so let's count the carbons here. How many carbons do we have in the reactant?
One, two, three, four, five. One, two, three, four, five, six. So we added, and we can't use MGBR, so we have to use NaCN,
Right, and why can't we use MgBr?
acidic hydrogen on the.
Yeah, right here. Acidic cannot use MgBr. So the first thing is NaCN, HCl, which you do SN2 reaction and convert the bromine into a nitrile.
Nitrile.
Mhm. Okay. And now we have the right amount of carbons that we wanted. One, two, three, four, five, six. And then there's only one last step here.
The OH, it's the OH minus, it's the OH minus thing. Wait. OH minus H2O and heat.
Uh-huh. And then second step.
Oh, acid workup.
Yep, acid recurve.
Oh,
And
I
that's it.
cooked, I cooked. 7 points.
Yeah, 7 points, 7 points, Robin. Let's go.
So we have a nitrile.
Yep, nitrile.
So so we have a nitrile, and then we end with a carboxylic acid with a amine on it, right?
Right. And where is this amine located at? What carbon relative to
The
the carboxylic acid? Right, the alpha carbon. And this can come from the NH3 3-day thing that you saw.
Yeah,
And this could come from the bromine in the alpha carbon. And what reaction would brominate the alpha carbon?
alpha halogenation HVZ.
Yeah, HVZ. And the reagents for those would be
HVZ is Br2 and PBR PB or P trace.
yeah, Br2 and P trace. Okay. So now we have to convert this 1, 2, 3, 4 carbon molecule into a 3 carbon molecule. So we have to get rid of one
Moving
molecule.
carbon bonds.
Yeah, we're gonna get rid of one instead of adding one. So you know how usually we want to add one carbon carboxylic acids, and those are like the two methods that we could use, NaCN or the Grignard CO2 route. Uh this case we're gonna get rid of one carbon, and this is gonna go back to 118B reaction.
Yeah, no idea.
Yeah. So let me just show you here. The first thing that we're gonna do is convert this nitrile into a carboxylic acid. What reagent do you think we would use to convert this nitrile into a carboxylic acid?
A nitrile into a carboxylic acid?
Mhm.
Like how? Let me see. Nitrile into carboxylic acid. Um, Nitrile into carboxylic acid. Wait. OH minus H2O and heat.
And the second step?
Acid, acid workup.
Yep, acid workup. That's right. That's right. Okay. Now we have our carboxylic acid. Um. Okay. Okay. So you know how we got rid of one carbon, right? We like got we lost a carbon. We came from 4 carbons to 3 carbons here.
Yeah.
118B reaction, a reaction that loses a carbon or cuts a carbon is ozonolysis. Remember ozonolysis?
No way. Ozone.
Ozonolysis is make a comeback.
Okay, ozone. Yeah. It's
Uh-huh.
just added the reagents.
Right. So um you know how we have like 4 carbon chain like that?
Yeah.
Ozonolysis, the reagents are gonna be O3, the second step, sulfur, CH3, 2. And what do you think this ozonolysis thing would do to this alkene here?
It would cut it in half.
Yep, it would cut it in half and add oxygens on the ends like that.
Yeah.
So we would have this aldehyde there. And how would we convert this aldehyde into the carboxylic acid?
Aldehyde. Oh, the aldehyde to carboxylic acid is. Oh wait, I knew that aldehyde to carboxylic acid. You could use like Tollens, Phalings, and Bayer,
Oh yeah,
but
yeah, those things. But there's a 118A reaction that you could do. What's the oxidizing agent that you could do to fully oxidize this aldehyde into the carboxylic acid?
I don't remember.
Jones.
You could use Jones for that.
Yeah, you use Jones on aldehyde to convert it into carboxylic acid. So,
Okay.
uh, let's say you had a primary alcohol like this, and you use PCC. What product would you get?
For a primary alcohol, you get aldehyde.
Yep, aldehyde. If you wanted to convert this aldehyde into carboxylic acid, then you would use Jones.
Yeah.
But instead of doing that, you could just go straight from the primary alcohol to carboxylic acid using Jones straight away. But if you want like like for some reason you needed this aldehyde, you could just convert this aldehyde into carboxylic acid using Jones too.
Yeah.
Mhm. Okay, so now we have to convert this carboxylic acid into this alkene here. Okay,
That's more of the old reactions.
yeah, these are more the old reactions. So you know how when we create alkenes, we did like E2 reactions or E1 reactions with
Yeah.
the base. Um, let's go back here. Let's say this is Br. We use the base like LDA or NaNH2, like any base that would do E2 reaction where this base will deprotonate that hydrogen, form the double bond there, and kick out the leaving group. Does that sound familiar for 118A?
Yeah.
Mhm. So now we have to find a way to convert this carboxylic acid into the bromine here. This is like similar to the last synthesis we did here. So looking at the last
A
synthesis,
carb a carboxylic acid into a what?
into a bromine. So
PBr3?
PBr3 would work with an alcohol. So first we have to convert this carboxylic acid into an alcohol. And what reagents would that be?
LiH4, H4
Yeah.
plus.
Right.
For 17 points, this is a crazy ass synthesis.
I know there's so many steps. Look at this. What the heck? It's crazy. H. Okay, and now from here to the
PBr.
yeah, PBr3. And then that's it. Summarize this for you. This is hydrolysis. This is reduction. This is SN2 like. This is E2. This is ozonolysis. I don't know why I should put that here. This is 118B reaction. Oxidation. HVZ. SN2. So there was like one,
Bro,
two,
that's
three,
tough.
4, 5, 6, 7, 8 overall steps.
That's crazy.
That's crazy.
All
Okay,
right, strongest acid is the most stable thing. So, um, we got to look at which one's the withdrawing group. So we have three, all of them are withdrawing groups.
yep, all of them are withdrawing groups.
All of them are withdrawing groups. So now we're looking at position, right?
Yep.
Position like ortho, para, whatever. So for the first one, that one, the ortho, they're all withdrawn. It's all positive charges. There's a positive charge on the para position, right?
On the
Um,
first one.
yeah.
So on the first one here, that only works for benzene rings. Do we have a benzene ring on the first one?
No, we don't.
No.
Let's look at the benzene rings. The benzene
Yeah,
ring
yeah,
is
yeah.
number one. Benzene ring is
Yeah.
number one.
Let's look at the benzene rings here. Okay,
So
so
between the two benzene rings,
mhm.
the third one, that one is the most acidic because it has a positive charge on the para position.
Yeah, that's right. That's right.
And then the other benzene ring would most likely be number two,
Yeah.
right?
Because it creates full positive charges.
And now within these other random rings, um,
In this case, you don't look at resonance, you look at the inductive effect. What's more able to pull that negative charge and stabilize it? The one that's closer or the one that's farther?
closer, yeah.
Closer, right? Because nitrogen is electronegative. It's able to pull that negative charge more.
The
This is a
orthopara is only for benzene rings, right?
yeah, it's only for benzene rings. Right.
Yeah.
So what do you think is more stable? The one that is stabilized by the closer NO2 or the further NO2?
So the last one is stronger,
Yeah,
and then four.
you
Okay,
got it.
got
You
it, got
got
it.
it. Yeah.
And
Be
then
careful. Be careful. This is not a benzene ring.
just the
Yeah.
ring.